Hello, Algebra 2 Trig students. Mrs. Leopold here for Unit 6, Parent and Piecewise Functions, Lesson 2, Absolute Value Functions. This lesson appears to be a little shorter, but don't underestimate it. It's a little tricky. There's still a lot of information that you need to digest and absorb, and so make sure if this video isn't enough, then go see your teacher and make sure you ask lots of questions. But our main focus this entire lesson will be about absolute value functions. And remember, hopefully in your brain you're like, oh yeah, that's the v. So it is the function that looks like a v. So warm-up exercise, you can go ahead and try to do this on your own, or you can do it with me. So it says, consider the function f of x equals the absolute value of 2x minus 8 and then minus 5. Use what you know about reflections, dilations, and translations to sketch this graph. Okay, well, if I'm focusing on what I know about reflections and dilations and translations, then I'm going to try to rewrite this to help me so I can see where my vertex is, look at my vertical or horizontal dilations. So notice this x has a 2 in front of it. That's not helpful. I need to factor that out so I can actually see what my horizontal dilation is. So when I factor out my 2, I get x minus 4. And so now I can see that my vertex is going to be h comma k. That's my vertex. And that point will be 4, negative 5. So now I'm going to go to the right 4, down 5. The next part is interesting. You can either consider this a horizontal a horizontal dilation, right? So you could deal with the horizontal dilation. The horizontal dilation, remember, you do the opposite. So the opposite means that we used to go right 1 up 1, right 2 up 2, right 3 up 3. We would just go up by a factor of 1 or left like this. But the horizontal dilation says that instead of that, we're going to go up half that distance. So we go we're going to go to the right half the distance. So we're going to go to the right one and then, right half up 1 unit, right 1 up 2 units. That's a little confusing, and I've just kind of bobbled it up a little bit here and there. So what we could do to make our lives easier is we could take that 2, because I think vertical dilations are always a bit easier, but we could take that 2 and we could go ahead and move it on the outside of that absolute value. Remember, anytime we multiply on the inside of the absolute value or whatever number we're going to get, it's going to be positive. So I'm going to take that 2, I'm going to put it on the outside, and so I would have 2 times the quantity of x minus 4 and then minus 5. So now this is a vertical dilation, and your vertical dilation means we're going to stretch twice as high. And so also in your absolute value, remember that when you have it in this standard form, this a value is associated with your slope or the vertical dilation. So we call it the vertical dilation, or we call it the slope. Now the slope is only good for the right-hand side of the equation from that vertex point. So if its slope is 2, well, I'm going to put that 2 over 1. So I'm going to go up 2 to the right 1, up 2 to the right 1, up 2 to the right 1. That is what 1/2 of my absolute value graph will look like. The other half is just we reflect it over the vertical line that goes to the vertex. And so my other half, I'm just going to follow that same pattern. And so this is what the left-hand side of your absolute value graph looks like. Now, the next part says, use your graph to solve this equation. So this is saying, when will this equation that I just graphed equal 3? So I'm going to go through here at 3, and hopefully you can see we would have followed that same pattern. So what are the values of x? Well, one of the values is 0, and the other value is 6, 7, 8 is 8. So when will it have a y value of 3? It'll have a y value of 3 when x is equal to 0 and when x is equal to 8. And we used our graph. Now, One of the goals for this particular unit is going to be to actually know how to solve this algebraically, because you're not going to want to draw a graph to find those answers. So soon we're going to find out how to solve this algebraically. So solving absolute value equations. It says when solving absolute value equations, we have to find all points of intersection. Depending on the function, there could be two solutions like here and here. There could be one solution because it's just the tip of where it's intersecting is where the vertex is, or there could be no solutions because the graph is above whatever y value we're trying to make it become. So remember that when you have an absolute value graph and you're trying to set it equal to some y value, you could potentially have two solutions, right? This is the y value, where you could have one solution because it goes to the vertex of the absolute value, or your absolute value never intersects because it's above, or it's below and opening downward, right? So we could have two solutions, one solution, or no solutions. Now, this is obvious. It says it's more obvious when seen graphically, like we just did on that warm-up example, but now we're going to take that warm-up example and we're going to figure out how to solve algebraically. So the first thing you want to do is you want to isolate your absolute value. So how do I isolate this absolute value? Well, I move the -5 to the other side by adding 5 to each side. So when I add 5 to 3, I get 8. So now I have an absolute value of 2x minus 8 is equal to 8. Remember, we said that the absolute value symbols are talking about the distance from 0 on a number line. And we're either going to go to the right-hand side of the 0 to get a distance, or we're going to go to the left-hand side to find the distance. The right is a positive direction, and left is a negative direction. So what we need to do is we need to take this value that's within the absolute value, that's 2x minus 8, and set it equal to 8. Or we need to take the opposite, so we need to go in the opposite direction. So we're going to take the negative of that value and set it equal to 8. So again, we have the positive direction, so I just took whatever that value was inside and just put a plus sign in front of it, which means nothing changes. It's just 2x minus 8 equals 8. Or if I want to go in the negative direction, then I had to put a negative sign in front because that's switching the direction from the 0 so that we have our two answers. And from here, we just simply solve. So we would get one solution of 8, and now I could divide each side by -1. So I get 2x minus 8 equals -8. So 2x equals 0. Therefore, x equals 0 is my other option. Or I could have distributed, right? I could have distributed the negative to get this, subtracted 8 from both sides, and so I still would have gotten 0. So that is how we solve it algebraically. Again, this is going to be very important. You write it how you see it right here, whatever this was, and then you take the opposite because you're going in the opposite direction from 0. So the positive direction and then the negative direction, or the right and to the left. So let's try it. It says solve the following absolute value equations algebraically. Check your answers with a graph. So if you want to check your answers at the end with a graph, you can. So you've seen me demonstrate one. You could pause now and try this one on your own, or you can follow along with me. Okay, step number 1 is to isolate your absolute value. So the first thing I'm going to do is move my -6 to the other side to make that a +6. Then I want to put the 3/2 on the other side. I'm dividing by 3/2, right? But if I divide by 3/2, 6 divided by 3/2 is the same as multiplying by 2/3. So you could have just said, well, I'm multiplying by 2/3 to cancel, or I'm multiplying by 2/3. So that's another way of thinking about it, is to multiply each side by 2/3. So now what do I end up with? I have the absolute value of x minus 1 equals, well, what is 6 times 2/3? Hopefully you're saying, okay, well, 3 goes into 6 2 times, and 2 times 2 is 4. So 6 times 2/3 is just 4. Now, what do we do? From 0, we're going to go to the right a certain amount, and we're going to go to the left. So we need to take this value, x minus 1, and set it equal to 4, or we need to take the opposite of that value and set it equal to 4. So I have x minus 1 is equal to 4, or I take the opposite of that value. So when I add 1 to both sides, I get a value of x equal to 5, or I can distribute, get negative x equals 3, or x equals negative 3. So I have two solutions, and they are 5 and negative 3. Now, if you wanted to do a quick sketch of the graph, I would encourage you to do that. So what do we have here? Well, I'm trying to graph this because that's going to be easiest is to isolate that. So what does that do? The absolute value of x minus 1, that's going to move to the right one, right? So if I'm just graphing y equals the absolute value of x minus 1 and y equals 4, and I'm seeing where these two intersect. So I move to the right one. Let's do different colors here. So I'll do this in red. And I would go right 1, up 1, right 2, up 2, etc. Or left 1, up 1, left 2, up 2. So that's my absolute value. And then I could go up to 1, 2, 3, 4 and find out where it intersected. So it's going to intersect at 5 and it's going to intersect at negative 3. So yes, our work is actually correct. You could also say to yourself, oh, this is the number 1. I shifted to the right one. Now I want to distance 4 units away. Well, 4 units away is going to take us to 5, or 4 units away is going to take us to negative 3. I went in the positive direction, which was this right here, or I went in the negative direction, which is why I have my negative, which is why I got negative 3. So hopefully all those things should make sense. They should connect. If that's not making sense, please ask your math teacher. We're happy to explain it to you. It's hard to do all of this in a video. Okay, I would pause and try the next one on your own, see how you do, or you can do it with me. The first thing we're going to do is try to isolate our absolute value. So what do I do first? I move my plus 5 to the other side, so I get 1 minus 5, which is negative 4. Then I divide each side by 2, so I get the absolute value of x plus 3 is equal to negative 2. Now, I hope alarm bells are going off in your head. I hope you're thinking, wait a minute, Mrs. Leopold, this isn't making any sense. How can I take the absolute value of some number and get a negative? The answer is you cannot take the absolute value of some number and get a negative result. So this is not possible. There is no solution. Right? So that is not possible. So you can write something like this, you can write this symbol, you can write no solution, but what does that mean? Well, if we were to graph that, so let's go ahead and graph it. This means we're going to have y equals the absolute value of x plus 3. That means we're going to move to the left 3 units, and we're going to have an absolute value that goes up like this because it's positive. So we have this, and then we have our second line is y equals negative 2. Well, this is y equals negative 2. Does the absolute value graph ever intersect that horizontal line at negative 2? No, it doesn't, which is why we have no solution. Those two are not going to intersect. Okay, so this is where things continue to get a little more complex. So again, please reach out to your math teacher if this is confusing. But we're going to talk about the inverse of an absolute function. So is the absolute value function one-to-one? Well, if you were going to quick sketch the absolute value function, you would have this v. So of course it's not one-to-one because it's failing the horizontal line test. So the horizontal line test fails, therefore it is not one-to-one. So therefore, will the inverse of an absolute graph be a function? No, it would be a graph on its side. It would fail the vertical line test, therefore it's not a function unless we restrict the domain. So we did this earlier in the year when we studied quadratics. Now you're going to have another opportunity to try to understand that restricting the domain. So here we go, example 3. It says sketch a graph of the function f of x equals 1/3 times the absolute value of x plus 2. All right, well, we're going to take this vertex. Our vertex is going to be what? It's going to be left 2, up and down 0, because there is no value here. So I go to the left 2. So this is my vertex of that graph. This value here is the slope on the right-hand side, from the vertex to the right-hand side. The slope is 1/3. So I go up 1 to the right 3, up 1 to the right 3, up 1 to the right 3. So this is the equation, this is the graph of that function. Now, what do? I reflect over this vertical line that goes to the vertex. So I go up 1 to the left 3, up 1 to the left 3, up 1 to the left 3. So this is the other half of that absolute value function. Now it says restrict the domain so that f of x is 1 to 1. Well, we want to restrict either the right-hand side or the left-hand side. And I'm going to be honest, it's going to be easier to restrict it to the right-hand side. So if I'm restricting to the right-hand side, then I'm going from -2 to positive infinity. I'm including -2 because that is where my vertex is, and that point is actually included and exists. So I'm going to go from -2 onward. Now, why am I going to take the right-hand side? Well, the right-hand side is the positive direction, so I can just take this function. Remember, if I went to the left-hand side, I would have to take the opposite value. I'd have to take the opposite value of this. Instead, because I went to the right-hand side, I can just simply take that equation, f of x, and I can just take the positive result instead. And so what do now? I switch the x and the y. I solve for y, and then I substitute in f to the -1 of x. So what am I going to do? I'm going to multiply each side by 3. So sorry, I'm running out of room. So I get 3x equals y plus 2. I'm leaving my 2 to the other side, so I get 3x minus 2. So the inverse function is 3x minus 2. Now, let's see if that is actually correct. We're going to graph, sorry, I skipped this, I didn't mean to. We're going to graph that function, but we're going to graph it pretending we don't know that this is what the function is algebraically. So what do you know about graphing an inverse function? Well, hopefully you remember that you take every ordered pair on the original function and you switch the x and y values. So that's when we have inverses. This is the original function, so every point on its inverse function is switching those ordered pairs. So this point right here, -2, 0, would become 0, -2. And this point right here, 1, 1, well, switching 1, 1 just becomes 1, 1. And this point right here is 1, 2, 3, 4, 2. So it's going to be 2, 1, 2, 3, 4. So this is my inverse function in red. And this right here is the original function. Sorry, and that we've restricted the domain, and now this blue part that I just went over would be irrelevant, right? Because we've restricted the domain. So really, I'm just focusing on this bit here to the left-hand side. Sorry, to the right-hand side. Sorry, I was erasing on the left, so that would be it. So there are my two functions, the function and its inverse, graphed right there on the graph. So the purple is the original function, and the red is the inverse. Now let's see. Was it in fact this equation of the line? So this is the y-intercept, which is -2. This is the slope, which is +3. So yes, that did indeed work. So what did I do? I restricted this original function to the right-hand side only. I restricted to the right-hand side, which means I had to indicate that with my domain restriction. Then my domain restriction impacted how I took the answer down here, which means I only had to take this positive result. So there's an invisible plus sign in front of this that we don't write. We only need to put the minus sign if we ended up going to the left-hand side of the graph. And so if we went to the left-hand side of the graph, that would be fine. We could still graph it and do all of this stuff. It would just be, would have to make sure you put a negative sign in here when you switch the x and y and resolved. So we'll do that later. But for now, if they give you an option, I would always go with the right-hand side. Okay, so this is one of those where we're kind of forcing your hand. So it says find the inverse of this function where f of x equals 2/3 times the absolute value of x minus 3 plus 1 on the domain from negative infinity to 3. So we're going from negative infinity all the way to 3. So we're looking at the left-hand side of the equation, which means we're going to have to do something with the negative portion of this graph, right? So we're going to have to find the inverse, which is going to be the negative side. So how are we going to do that? Well, we have the equation. It's right here. So what do? We take that equation and we are going to, I'm just going to rewrite it down here. I have to take the opposite of that equation, right? So I'm going to take either, this is going to have a plus or a minus sign in front of it. So I am going to take the negative side because that would give me the domain from negative infinity to 3. So I'm going to have switch my x and y, but now I have to put the negative in front of the 2/3 because I'm talking about the left-hand side. And once you do that, the rest is going to be the same. So again, you're making a choice. Is it plus or minus? Because when you graph whatever the absolute value is, you have the right-hand side, which is the positive slope, or you have the left-hand side, which is the negative slope. And so I want the left-hand side, so I want the negative slope. So now we go ahead and solve. You can treat this absolute value now as just a parentheses. It doesn't really impact it because we already made our choice. So we don't even need to make the absolute value sign anymore. We can just make parentheses. So now what do? I multiply each side by the reciprocal, right? So that's how I get rid of it. So I multiply by negative 3/2, so that cancels. So I have negative 3/2 times the quantity of x minus 1 equals y minus 3. My last step, as you know, I love to do the combo finish. So replace y with f to the negative 1 of x and move the minus 3 to the other side. So this would be my final, or would it be the final equation? Actually, it's not. We're missing something. So let's kind of figure out why. So here, if we look at the original function was this absolute value of equal go to the right 3, up 1. So here we have it. We are only taking the left-hand side due to this domain restriction. So I'm only going to go from negative infinity to 3. I'm not worried about the slope. Yes, I'm just sketching it. So that's the graph. So now if I were to graph this function down here, okay, so this is how I'm going to graph. This is an equation of a line, I hope you realize here. There's no absolute value symbol, there's no squares, there's no cubes, there's no cube roots, no square roots. It's just an equation of a line. But what I can do with this equation of a line is I can still think of it as in terms of a vertex, right, h and k. So I go right 1, up 3, and then because it's a negative slope, I'm going to go down 3, 1, 2, 3, right 2, and so this is how that equation of a line would look. Or would it? So why did I go down instead of up, and is that actually the correct answer? So remember, inverses have to be reflected over this line, y equals x, And I would say yes, the graph I drew, the blue graph and the sketch of the blue function and the sketch of the red function, they are reflective over that line y equals x. And so yes, I would say this is the proper direction. It was supposed to go down to the right. But then that means we can't say the domain is all real numbers. We actually have to restrict the domain here for this one. So it is essential that for this question, you restrict the domain. Well, where is the domain starting? It's starting at 1, and it is going onward to infinity. So 1, sorry, should be inclusive, so I have the hook in there, and it is going onward to infinity. This has to be included in your inverse notation, right? So not only is it the equation, -3/2 x minus 1 plus 3, but you must have this domain restriction. Again, it's a little tricky. You're going to need some time to digest it, absorb it, and then come back and ask questions, or ask questions anytime, whenever you get an opportunity. All right, use function composition to verify if the following are inverses of each other or not. So remember, function composition says if f of g of x equals g of f of x equals x, then they are inverses of each other. So we need to take this function and substitute it in here and see if it equals x, and then we need to take this entire function and substitute it in here and see if that makes it equal to x, and if that is true in both cases, then these are inverses of each other. Now please notice this is going to positive infinity, so when I input this function into g of x, I'm only going to take the positive side, or the right-hand side. So I'm going to put a plus 1/2, then ignore the absolute values, make them parentheses. And then this is associated with the proper side, so you're not having to worry about the positive or negative. You can just insert the 2x plus 5. So go ahead and pause and try this algebra on your own and see how you do. Okay, hopefully you saw that these two functions are indeed inverses of each other. When I substituted in g of x and for the x of f of x, that was pretty straightforward, and I just got x as my final answer. When I inserted f of x into the x of g of x, it was a little more complex, so I had to put that in here. Then I distributed 1/2 times x, 1/2 times 1 to get 1/2 x plus 1/2 minus 3. Then I distributed the 2, so I got x plus 1 minus 6, and then my plus 5 is just hanging out here by itself. And so plus 1 minus 6 plus 5 cancel each other out, so I got x again. So because you have to make this statement, because f of g of x equals g of f of x equals x, then the two functions are indeed inverses of each other. So now, our last little bit is about the absolute value of an entire function. So what happens when we put an entire function or ask you to take the absolute value of an entire function, right? So that's different. So of an entire function. Well, if we gave you this function here on the left-hand side, we're eventually going to start studying piecewise functions. And this function on the left-hand side here, f of x, is a piecewise function. You have a couple of different things going on. We have a line segment here, a different line segment, another line segment, and a fourth line segment. So here are some ordered pairs. When I plug in these x values, I would get these y values. But if I take the absolute value of that entire function, now notice I'm not giving you what that function is algebraically, I'm just giving you ordered pairs, and we wouldn't even give you this table. But if you were taking the absolute value, that means every y value would have to be a positive result. So anything that is down here on the negative y value side, this section, all of these values have to become positive y values. So they have to pop up here to the positive side. So every y value needs to be in the positive side because I have these absolute value symbols right here. So what am I going to do? Well, I'm going to keep this section. This is going through 4, so I have 4. I go up to here's 7. It looks like 7, 7, or 7, sorry, 4. and then I go out to 10. So this section, we're all positive y values, so that's going to stay the same. And then this section over here, right, it looks like it goes through negative 7, 0, and then it's going to go up here to 10 at 4. Is it 4? No, it's 5. Sorry, so that's the section equivalent over here. And so then what happens to the blue section? Well, it has to pretty much reflect over the y-axis, right? All of those need to become positive y values. So this little straight section is going to be important. We're going from negative 4 to 0, and those y values were negative 5, so now all those y values are going to be positive 5. And then I'm just going to connect here and connect here. So basically I took this section right here and I reflected it up over the y-axis so that every y value would be positive. So at 0 it's going to be positive 5, at negative 4 it's going to be positive 5. So all of these values are positive, everything else stays the same, but at 0 I went up positive 5, and at negative 4 I went up positive 5. And all those y values in between have to stay positive. So that's what your graph would look like. So not difficult, right? Just knowing that all of your y values have to be positive, so I'm just reflecting it over, any negative value has to be reflected over the x-axis. So what can you conclude about the f of x and the absolute value? And I've just said it many, many, many times, and that is reflecting over the x-axis, and all of your y values will now become positive y values. So go ahead and try this one on your own. I would pause and then check back with me when you're done. So are these what your two graphs look like? So I took the original one, right? I sketched it, has a vertex at 2, negative 4. There's no stretch value, so it's just 1 to 1, 2 to 4, 1 to 1, 2 to 4. So this is what my original graph looked like. But now, of course, I have to take this red section down here, and I need to reflect it over the x-axis. All these y values are negative, and I need to make them positive because I'm taking the absolute value of that function. So now every single y value is indeed positive, and that's exactly what we want. And so this would be the sketch of the absolute value of f of x. Hope this helps. Again, there's a lot to kind of understand and learn today, so please ask us math teachers if you have any questions. Bye.